paradigm shift in short, the overthrow of rules that are absurd to even question. I think he is one of the most prominent representatives of this term in the world of science. Don't worry, I'm not going to say Einstein. We've already talked a lot about what kind of change he caused. But considering his time and the change he caused, this name, Michael Faraday, is our undocumented genius, Michael Faraday. His discoveries in electricity and magnetism were incredible. He laid the foundations of electromagnetism and closed an era and opened a new one in the world of science. It wouldn't be too much of an exaggeration to say that all the developments that came after him were at some point thanks to him, including quantum physics. Yes, quantum physics, and beyond. But with Faraday's fire, our perception of the universe undergoes an incredible change. With this video, we are approaching the end point of all this change. I should warn you from the beginning. As always, in this video, I am planning a serious attack on conventional wisdom, classical physics, and the way we perceive the universe. Fasten your seatbelts. Beyond all of Faraday's experiments and discoveries, the biggest indicator of the change he caused are fields, electric field and magnetic field. Think about it. We've even normalized it a bit, but think about magnets. You are bringing them closer to each other. You are trying to touch the same poles. But there is a force between them. You feel it. In that space, there's something in that space. It's not empty, actually. There's a space there. We learn this at school. It's very simple. We learn and we pass. But I think we don't give it enough credit. I don't think we realize how radical this finding and phenomenon is. I mean, I've reached this age and it still seems like magic to me. But there is an explanation. This is where Faraday's genius comes in. He explains these invisible fields to us. Everything that is happening around us is happening because of these fields. He said this in front of people at the Royal Institution. He would prove it by moving the needle of a measuring device on the other side of the table with the motion created by the magnetic field generated by the electricity he applied to a coil. Imagine the astonishment of the people in that hall. The person can move an object from a distance without touching it. Magic exclamation mark today. You can pick up your phone and call and talk to someone on the other side of the world. This was the first demonstration of this possibility, this marvelous development in history. The indicator needle moving left and right on the other side of the table. South. With these invisible fields, you could move distant objects. You could influence them. You could communicate through these fields. Whatever we can do in the modern world today, we do it thanks to these fields. This is the kind of legacy Faraday left. It would not end with this. In one of these public lectures, which he continued for a long time, Faraday finishes about 20 minutes early. In the last 20 minutes, he starts brainstorming in a completely improvised way. For 20 minutes, he was going to talk about how the electric and magnetic fields he had discovered did not stop there, and that in fact everything humanity had ever seen owed to these waves. In short, he would say that light is also an electromagnetic wave. People who had admired all his experiments laughed seriously at this part. They would say, "It's not that much." About 50 years later, thanks to Maxwell and Hertz, we would learn that he was right about that too. That light is a wave, even if he couldn't see it himself. In short, there were not just particles in the universe. What we call matter was only the visible and tactile part of our experience. There were also fields that filled all the remaining parts, spread all over the universe. But Faraday could not have guessed how important these fields were, and nobody could. By the 1920s, with the contributions of names like Heisenberg and Schrödinger, we were going to understand that the universe worked in a very, very different way, and we were going to be introduced to quantum mechanics. You already know that we have talked a lot about these years of quantum mechanics and its revolutionary developments. Be sure to take a look at these videos, because with this video, as I said at the beginning, things get very, very, very complicated. To recall the most striking part of quantum mechanics, energy is not continuous. What we call energy exists in very small packages. That's more or less what quantum means. Packet. But the real trouble starts when you take the rules of quantum mechanics, which sees energy in packets, and apply them to Faraday's fields. Because these fields that go on and on and on and on. And when we combine these two, we come up with a very crazy theory. quantum field theory. The first result emerges when we apply quantum theory to light, which is also an electromagnetic wave. When we analyze these waves, we see that these waves, in packets, we call them photons. And here's the real magic. What if I told you this principle applies to every particle in the universe? For example, in the room you're in right now, there is an electron field. In fact, everywhere in the universe. The waves in this electron field turn into packets at certain points according to the rules of quantum mechanics. We call these packets electrons. So the electrons in your body are just packets of the same electron field in the universe. The electrons in you and the electrons in all the people. The electrons of any object are different expressions of the same wave. We are actually speaking scientifically when we say that we are all interconnected. It's like waves in the ocean. They look different, but they are all part of the same giant ocean. And it doesn't stop there. The neutrons and protons and quarks are part of a quark field, or any particle you can think of. Every single one of them, wavelets in a field. So, hold on tight. Quantum field theory tells us there are no particles in the universe. There are fields and ripples in these fields. That's all there is. It's a bit much, isn't it? I know. Don't worry. I'll try to explain as much as possible what it all means. I'm not saying it will be easy, but we'll try together. At this point, I'll show you a video first. A video of nothingness. Yeah. Chuckles. Of nothingness. A computer-generated simulation. Imagine a box, all the particles inside. When you empty it of everything, physicists call it a vacuum. This is what happens when you create a vacuum, a complete void. But even when we remove all the particles, you can see that it's not empty. Nothingness is not boring at all. There is still a field. Fields are everywhere. And the strangest thing is that this vibrating nothingness also follows some rules. The rules of quantum physics. The Heisenberg uncertainty principle in particular. This principle tells us this: you can't stand still, you have to move. There are lessons to be learned from this principle on a personal level, but in our case, the field in the nothingness that you see here obeys this rule. It has to fit. Even if there is nothing there, it has to ripple, it has to bubble, it has to move. There is a name for it. Quantum vacuum fluctuations, and these are the most difficult, is one of the phenomena. There's even a cash prize, it's no joke. If you're at all interested in math, you're probably one of the hardest. You've heard of the hardest 6 problem in math. Actually, there were 7, but a crazy Russian solved one. Here are 6 almost solved. There are math problems that seem impossible, and quantum fluctuations is one of them. We're math rebels. We're not talking about showing these fluctuations in a simulation. I'm talking about being able to explain this movement of nothingness. He refused to explain the rules by which he acted. Maybe you can ask the question, are we sure these waves exist? Yes, we are. The most obvious proof is the Casimir Effect. But the subject is already complicated. I'll leave this part to your research. Don't forget to research the Casimir Effect after the video's over. I mean, the basis of everything in the universe is not atoms and so on. The basis of matter, the basis of everything, is these fields. And the fluctuations in these fields, we're all made of quantum fields, okay? Okay, let's go a little deeper. We remember the periodic table, don't we? A list of the elements that make up everything in the universe. Isn't that lovely? It's a great classification. But unfortunately, we have to forget it, because it has no meaning anymore. I mean, of course it is used in daily life, in the calculations we do in laboratories, in chemical reactions. It will continue to be used, but it has no place in the quantum universe. Let's look at the actual periodic table with you. This is it. These are the particles that make up everything in the universe. The electron and 2 quarks. And that's it. That's all we need to know. And then there are neutrinos. Let's not forget them. They have nothing to do with the formation of matter, but billions of them are passing through all of us as we sit here. They are a bit different. They pass through the world too. They are quite asocial, but we'll talk about that later. What we need to know is the electron and 1 up quark and 1 down quark. Why they call them up and down doesn't make much sense. I guess they couldn't come up with a cool name. But if it stayed here, we could understand it to some extent. But then we found out there were 3 of them. Muon and tau, which behave just like electrons but with more mass. The muon and tau neutrinos, which are the same as neutrinos but more massive. After the lower quark, the strange quark and the bottom quark after the upper quark, the talisman quark and the top quark. Why are they there? Why do they exist? We have no idea. It's one of the great mysteries of science. But these 12 particles at the top are the particles that make up everything in the universe as far as we know. And so there are 12 fields. These particles are part of their own 12 separate fields. And these fields interact with each other with the 3-9-3-9-3-9-4 fundamental forces in the universe: gravity, electromagnetism, strong nuclear force, and weak nuclear force. And each of these forces is a separate field in its own right. So there are 12 fields of matter in total. There are 4 force fields. We are talking about the interaction of 16 fields in total. A fluctuation in one field, for example in the electron field, can cause fluctuations in other fields. It causes a fluctuation in the electromagnetic field, and then it triggers the quark field, and we have a dance going on between these fields. A dance of fields. And this dance sets everything in motion. This dance tells us one of the most comprehensive theories about the universe that humanity has come up with. Even though the name doesn't sound very cool, this is what we call the Standard Model. At least we thought so. We were missing a piece of the puzzle. What gave matter its mass? The waves in the field made the electron, but what gave it mass? This is where the incredible discovery at the Large Hadron Collider has enlightened us. The Higgs field. We've talked a lot about this before. This explained what gives a particle its mass. The missing piece of our Standard Model was complete. One more area. Now at this point, let's look at a formula together. Let's take a look at a melody. We don't need to understand it. But you know what we have here? This formula is the most successful formula we have right now, the theory of everything. As I said, we don't need to understand it. Most scientists don't understand it anyway. You can use it whenever you need it. It's amazing that it even exists. Because it may sound crazy, but this formula, in history, we've ever done, that correctly predicts the outcome of every scientific experiment we've ever done. Everything. All of it. It's all in this formula. Let's take a look at it piece by piece. Here we have Einstein's equation of gravitation. So when you solve this part, you can calculate how far an apple will fall from a tree, or how a black hole forms and emits gravitational waves into the universe. Then comes Maxwell, with his equation for electromagnetism, from Faraday to Hertz. Everything we do about electromagnetism is in this section. Then the strong and weak nuclear force. Then comes Paul Dirac. He talks about matter, the 12 particles that make up matter. Then comes the Higgs boson. He explains how matter interacts with the Higgs field. Everything is here. All scientific developments are here. Everyone is here. This is the limit of what humanity knows right now. Welcome to the pinnacle of our current knowledge. I mean, this is the point where all the big names have joined hands. So is this the last stop? Let me put it this way. We're not even close. Because now at this point, it's time to talk about what I'm going to talk about later on. Dark matter and dark energy, even antimatter. Because there is no dark matter in this equation, no dark energy. We know very well that they are there, but we cannot see them. They're there, but they're hiding. They've been there since the first second, right after the Big Bang. Anyway, I'll talk about these issues in future videos. Do you remember this photo? We said it was a baby picture of the universe. It's a picture of the first 380,000 years of the universe. During this period, everything was on fire. But zoom in a little closer and you'll see some colder spots. What's around here? Yes, it's true, quantum waves. These spaces are completely empty, nothingness. But we know that nothing is not nothing. But what is? This is our wall. It's a wall we haven't been able to overcome so far. So what are we doing? We're looking for a clue at the Large Hadron Collider. After finding the Higgs field, it was suspended for 2 years, and it was reopened with twice the power. We haven't found anything since then. So what exactly are we looking for? Supersymmetry and strings. If we've reached the limits of what we know, what's next? It means that we, all of us together, can now break the strings on some videos. We still have a long way to go and a lot to talk about. Are you as excited as I am? Above all, I say, I am glad there is science. And as always, I say, I'm glad you're here. Until we meet again. Love,